Good evening, everyone. This is today's class, lecture number 23 about heat and mass transfer, ME145. And today we are going to solve some problems about the topic we covered 2 days ago about heat exchangers. First of all, I apologize for the inconvenience that happened today. I wasn't really feeling that well in the morning, so I wasn't able to come to class. But anyway, this video should include what I was going to cover in class, all of it. I was going to solve two problems today, so we will solve them together step by step, as if we are in class. And also, we were supposed to have a clicker quiz, which we will also go over and solve the problem included in it. Of course, it's not going to be an actual quiz for you, but we will go over the problem and solve it. Anyway, so we will have three problems, two actual problems, and the quiz problem. So let's get started with this. And our first problem is problem number 1114 in your textbook. And if we start to read the problem together, the problem says, a shell and tube exchanger, two shells, four tube passes, is used to heat 10,000 kilograms per hour of pressurized water from 35 to 120 degrees Celsius with 500 kilograms per hour pressurized water entering the exchanger at 300 degrees Celsius. If the overall heat transfer coefficient is 1500 watts per meter squared kelvins, determine the required heat exchanger area. So this is a problem where we have a shell and tube exchanger. We have multi-shells, multi-passes, so two shell passes, four tube passes. In this case, we need to find out the design parameter for heat exchanger, which is the surface area required to do a certain job. So what we have is a shell and tube heat exchanger, two shells, four tubes. We have this heat exchanger heating up 10,000 kilograms per hour of pressurized water. So that's the cold fluid, pressurized water. The mass flow rate for that is given, 10,000 kilograms per hour, from 35 degrees Celsius to 120 degrees Celsius. So this is our cold temperature at the inlet, and the temperature of the cold fluid at the exit as well are given, 35 and 120 respectively, while the mass flow rate for the cold fluid is 10,000 kilograms per hour. For the hot fluid, we do have water, hot water. The mass flow rate for that is given, which is 5,000 kilograms per hour, so m dot h is 5,000 kilograms per hour. And also we have the inlet temperature for that hot fluid, which is 300 degrees Celsius, but we do not know the exit temperature, TH outlet. We have the overall heat transfer coefficient given to us, U, and this is equal to 1500 watts per meter squared kelvins. These are the given information to us. What we need to find is the required heat transfer area for our heat exchanger, or AS. So in this case, we have two fluids. We have two streams of fluids: pressurized water, which is cold, hot water, that's the hot fluid. So we need to find the properties for these two fluids. And the properties for the fluid are obtained at the average temperatures. So, for example, for the cold fluid, the average temperature between T cold in and T cold out. And this average temperature, if you calculate it, take the average and convert it to Kelvin, that would be around 350 Kelvin. So you go to the table for water properties, and this is table A6, and you find the CP for the water. CP for the cold water is 4195 joules per kilograms Kelvin. Same thing is going to be done for the hot water stream, but the problem here is that we only have the inlet temperature. So in order to find the average temperature, TH bar or TH average, you need to assume a value for TH out. So our assumption would be a temperature, it should be like that. the exit temperature for the hot water should be definitely less than the inlet temperature because it's cooling down. But it needs to be greater than the inlet temperature for the cold water because we have not reached equilibrium. We have not reached the maximum possible way with the maximum possible cooling down to the minimum possible temperature, which is TCI. So it should be greater than 300, higher than 35. So my assumption here, I would assume, as a first trial, I would assume the TH out to be 100 degrees Celsius. Therefore, based on this assumption, my average temperature for the hot water is 500 degrees, is 500 kelvins. So I have this assumption. I find my CP based on that assumption, and from the table it is 4,660 joules per kilograms Kelvin. I would calculate that, and at some point I would be able to calculate TH out, and then I would compare it with my assumption. If it's too far off, I wouldn't think so because our assumption is kind of makes sense. We understand the temperature should be less than THI but greater than TCI, so we assume something in between the two. So I would say that our assumption is for now it makes sense. So I wouldn't expect too much deviation when I calculate the actual TH out. Anyway, if we do that, if we find significant deviation, then we do a second trial. If we don't find a huge deviation between our assumption and the actual temperature, then we will live with it. So based on the assumption, we found CP for the hot stream, and we found CP on the cold stream using no assumptions at all because we have all we need. So now we have the properties for the two streams. So in this case, let's get started with the solution of the problem. In this case, since we have our U, we have shell and tube heat exchanger. We usually use the effectiveness NTU method. It's always possible to use the other method as well, the theta LMTD method, but this one is preferred for the shell and tube heat exchangers. So that's the one we are going to use. So based on this method, we usually try to find the effectiveness and then find the NTU from it. Since the effectiveness is simply defined as the actual heat transfer divided by the maximum possible heat transfer. So this is an easy task to do. So let's calculate the energy balance on one of the fluids. Let's take the cold fluid and calculate the amount of heat it receives. By the way, the amount of heat the cold fluid receives is equal to the amount of heat the hot fluid loses. So Q, which is the amount of heat, for the cold fluid, now we are analyzing the cold fluid, it is equal to m dot cold times Cp cold times T cold outlet minus T cold inlet, mc delta T for the cold fluid. So the mass flow rate for the cold fluid is given as 10,000 kilograms per hour, converted to kilograms per second by dividing by 3,600 seconds per hour, so that this m dot becomes kilograms per second, multiplied by Cp for the cold fluid, 4,195 joules per kilograms Kelvin, times the temperature difference for that cold fluid, and it is 120 degrees Celsius minus 35 degrees Celsius. The reason Kelvin is written here because the temperature difference in Celsius is the same as Kelvin, so it doesn't matter. Therefore, the actual heat transfer that's happening, the actual heat received by our cold fluid and lost by the hot fluid is 9.905 times 10 to the 5th watts. So that is our first step. We calculated the actual Q. The next step is to use that Q. Remember, what I said is the Q, the heat received by the cold fluid, is actually the heat lost by the hot fluid. So I can apply the same energy balance on the hot fluid using the Q I know now to find what's missing. And the only thing that's missing is TH out, the hot temperature. So now it's time to test our assumption. We assumed it to be 150. So let's calculate TH out. So it's equal to TH in minus Q over m dot H CPH. Since Q is equal to m dot H CPH, TH in minus TH out. and the Q is the same as the Q we just calculated for the cold fluid. And therefore, the only thing that's missing is TH out, and this is going to be equal to TH in, 300 Celsius, minus Q, 9.905 times 10 to the 5th watts, divided by CP, actually divided by the mass flow rate for the hot fluid, which is 5,000 kilograms per second, converted to kilograms per, it was 5,000 kilograms per hour, converted to kilograms per second by dividing it by 3,600 seconds per hour. I also divide this by Cp for the hot stream, which we assume to be 4,660 joules per kilograms Kelvin. This calculation gives us TH out to be 147 degrees Celsius. So recall that we assumed it to be 150 Celsius. So I would say that the difference is not that much. 3 degrees would not affect our CP that much, and therefore I can live with that assumption. I can live with the CP I calculated earlier. I don't need to do any more iterations. So that's my TH out. Now, my next step is to be able to find our Q maximum. Remember that the effectiveness epsilon is equal to Q over Q maximum. I have my Q. I still need my Q maximum. So therefore, TH bar becomes, instead of being 500 kelvins, it becomes 497 kelvins. That should be the proper temperature for evaluating properties. But because the difference is not too much, like I said, I would keep using CPH we calculated, which is 4,660. Because the difference, if you calculate it based on the new TH bar, the difference would not be that much. So I will keep using that one. Anyway, I'm going to be now calculating the C, the heat capacity, capital C, for both fluids. So I have to calculate CC and CH, so that I can decide which is C minimum. So my CC is m dot cold, C cold is m dot cold times CP cold. Again, 10,000 kilograms per hour divided by 3,600 seconds per hour, multiplied by the CP for cold fluid, 4,195 joules per kilograms Kelvin. It gives us a heat capacity for the cold fluid of 11,650 watts per Kelvin. Same thing to be done with the hot fluid. Capital C hot is equal to m dot hot times CP hot. So 5,000 kilograms per hour divided by 3,600 seconds per hour. That's the m dot, multiplied by CPH, and again I'm keeping the one I assumed in the beginning because there is not too much difference. So 4,660 joules per kilograms Kelvin. Then I find the capital CH, or the heat capacity for the hot fluid, to be 6,470 watts per Kelvin. So that's definitely the lower or the minimum of the two. So CH is C minimum. And also I would need to calculate CR, which is the ratio between the two C's, because it's a very important parameter. If you remember from 2 days ago when we were showing the correlations for calculating the effectiveness from NTU and vice versa, the main parameter included in these correlations is the CR, which is the ratio between C minimum and C maximum. So therefore, this ratio is 6,470 divided by 11,650. So the CR, or the heat capacity ratio, should be 0.555. So now we have our C minimum, we have our CR. So C minimum, I'm going to use it to calculate my Q maximum right now. So Q maximum is C minimum times the maximum possible temperature difference. So the highest temperature in the cycle minus the lowest temperature in the cycle. THI minus TCI. T cold in minus T hot in minus T cold in. So C minimum is 6,470 watts per Kelvin, multiplied by the maximum possible temperature difference, 300 Celsius minus 35 degrees Celsius. Then the maximum possible heat transfer in this heat exchanger, Qmax, is 1.75 megawatts, or 1.75 times 10 to the 6 watts. And therefore, I already calculated the actual Q. at the very first step of my solution here. So I can calculate the effectiveness now, or epsilon, because it's the ratio between Q actual divided by the ratio between Q actual and Q maximum. So my actual Q, my actual heat rate, is 9.905 times 10 to the 5th watts, divided by the maximum possible Q, which is 1.72 times 10 to the 6th watts, and this ratio, or the effectiveness in this case, is going to be 0.577. So now I have my effectiveness. I know the type of the heat exchanger. Therefore, I can go to my correlations table and find the right correlation to be able to calculate my NTU, number of transfer units, from the effectiveness, which is epsilon. That's my next step for now. So if I take a look at the table, I would go to the correlations for shell and tube heat exchangers. So we have correlations for one shell pass, and we have correlations for n shell passes. Our heat exchanger is 2 shell passes and 4 tube passes, so it's n shell passes. So let's see what this says. It says use equations 1130b and 1130c, which are these two equations up there. The same equations used for the one shell pass with a little modification. I would use epsilon 1 to be f minus 1 over f minus CR, where f is calculated from that expression here. So once I find f, I can find epsilon 1. Once I can find epsilon 1, I go to this equation to find E. Once I find E, I can calculate NTU for one shell pass. And then finally, the NTU for n shell passes is actually equal to n times the NTU for one shell pass. So that's the sequence here. I start with the F. I go from the F to calculate epsilon 1. Epsilon 1 is used to calculate E. E is used to calculate NTU one shell pass. And then finally, this is multiplied by the number of shell passes to give you the actual NTU for your case. Let's do this. And you can see that all the expressions include CR, where the CR is the heat capacity ratio we just calculated, C minimum over C maximum. So let's use these equations to find our NTU. So our F is calculated as epsilon CR minus 1 over epsilon minus 1. We have the epsilon, 0.555. We have the CR, actually the epsilon is 0.577. CR is 0.555, we calculated those earlier. N is the number of shell passes, and in this case N is equal to 2. We have 2 shell passes. So if we calculate your F, you'll find the F to be 1.27. Use the F to find the epsilon 1. These are corrections to the epsilon. So epsilon 1 is going to be equal to F. So this is the epsilon if one shell pass was used. The epsilon we calculated is for our actual heat exchanger for 2 shell passes. So epsilon 1 is the epsilon for the same heat exchanger if only one shell pass was used. So that's a correction. So it's F minus 1 over F minus CR. F is 1.27, CR is 0.555. Then you find your epsilon 1 to be 0.3776. And you see that epsilon for the effectiveness for one shell pass is less than the effectiveness we calculated for the 2 shell passes of 0.577. Now we can use the corrected effectiveness to find the E, where E is calculated as 2 over epsilon 1 minus 1 plus CR divided by 1 plus CR squared to the power of half. And therefore, our E is going to be 3.29. Now I can use this E to find NTU1. And from NTU1, I just multiplied by N to find the NTU for our heat exchanger with multiple, or in this case 2, shell passes. So my NTU is N times minus 1 times 1 plus CR squared, and this bracket is to the power of minus half, multiplied by the natural log of the ratio E minus 1 over E plus 1. We have everything. We have our E, we have our CR, we have the N equal to 2, the number of shell passes. Therefore, the NTU for my heat exchanger is 1.1. Now I can use my NTU I just calculated and use the definition of NTU, which, as we recall, NTU is equivalent to UA divided by C minimum. U, if you remember, is the overall heat transfer coefficient. C minimum is the minimum heat capacity, and A is the surface area. I have my U, it's given 5,000, I remember, actually 1,500, 1,500 watts per meter squared Kelvin. And C minimum, we calculated it before. The only thing that's missing in this equation is A, and that's the surface area that I want to calculate from the beginning of the problem. So if you play with this equation a little bit, then you find finally that the surface area is equal to NTU times C minimum divided by U. NTU is 1.1, C minimum is 6,470 watts per Kelvin. Divide that by the overall heat transfer coefficient given to us in the problem statement, which is 1,500 watts per meter squared Kelvin. Do the math, and then you'd find the required surface area for this heat transfer shown in the problem to happen is 4.75 meters squared. That is the total surface area required for the heat transfer in that heat exchanger. So that would be our first problem for today. Again, I remind you, if you have any questions about any step of the problem, please let me know by either just comment on the video, or you can always email me at any time. So if you just comment on the video, that would be also one way to let your colleagues know what your question is, and all of the people who see the video will be able to see the question and my answer to the question as well. So that would be, I would prefer that way, so that as if we are in the class and people get to listen to your questions and listen to my answers to the question as well. So that is the first problem for the day. Let's move forward to what comes next, which is the clicker quiz we were supposed to have today. So in this clicker quiz, the problem was as follows. We had hot oil with a CP of 2.1 kilojoules per kilograms Kelvin. That's our hot fluid. We already have the CP for it, so no tables needed. So CP is 2.1 kilojoules per kilograms Kelvin at 110 degrees Celsius. That's the inlet temperature of the hot oil, TH inlet. And 8 kilograms per second, that's the mass flow rate for the hot fluid, M dot H, is to be cooled in a heat exchanger by cold water. So I have the cold fluid to be cold water. It has a CP of 4.18 kilojoules per kilograms Kelvin. Entering at 10 degrees Celsius, so this is T cold in, 10 degrees Celsius, and at a rate of 2 kilograms per second. That's the mass flow rate. So M dot cold is 2 kilograms per second. The lowest temperature that oil can be cooled to in this heat exchanger is, I need TH out, but the minimum possible TH out. So that would be, I would imagine that it would be associated with the maximum possible heat transfer, Qmax. So Qmax gives us the maximum possible temperature difference. So for Q maximum, I would have the minimum possible exit temperature for the hot fluid, because the fluid cools down a lot. The temperature difference would be the maximum possible. So the minimum possible T hot out is one of the 5 options over here. 10 degrees Celsius, 33.5 degrees Celsius, 46.1 degrees Celsius, 60.2 degrees Celsius, and 71.4 degrees Celsius. So let's try to see how this problem is solved, and let's see which of these options could be correct. So for our hot oil, we have CP hot, 2.1 kilojoules per kilograms Kelvin, T hot at the inlet, 110 degrees Celsius, M dot H, or M dot hot, is 8 kilograms per second. But for the cold fluid, cold water, I have CP cold, 4.18 kilojoules per kilograms Kelvin. T cold in is 10 degrees Celsius. M dot cold is 2 kilograms per second. That's the information I have, and I would need to use this information to find the minimum possible T hot out. So here, since I'm dealing with the minimum possible temperature difference or the minimum possible outlet temperature, like I said, I would need to find the maximum possible heat transfer or heat rate. So to be able to do that, I would require C minimum. So to find C minimum, I need to calculate both C's for hot and cold fluids and to find the minimum of both. So I would start with the hot fluid. Capital T hot, or the heat capacity for the hot fluid, is m dot H times CPH. In this case, it's going to be 8 times 2.1, and the answer here would be 16.8 kilowatts per Kelvin. For the cold fluid, I do the same thing. C cold is going to be m dot C times Cp cold. I have 2 kilograms per second multiplied by 4.18 kilojoules per kilograms Kelvin. That would give us 8.36 kilowatts per Kelvin. And compared to the other one of 16.8, that would be less. So that would be the minimum of the two, and C cold becomes C minimum. So the maximum possible heat transfer would occur if for the fluid with the minimum heat capacity, which is the cold water now, if it was heated up from its inlet temperature of 10 degrees Celsius to the maximum possible temperature, which is the inlet temperature of our hot fluid, that would be the maximum possible temperature difference, and therefore the maximum possible heat rate. So Qmax is C minimum times the maximum possible temperature difference, THN minus T cold in. Always, the maximum possible temperature difference is the difference between the two fluids' temperatures at the inlets. So I have C minimum to be 8.36 kilowatts per Kelvin multiplied by the maximum possible temperature difference, THN 110 degrees Celsius minus T cold in 10 degrees Celsius, and therefore our Qmax is going to be 836 kilowatts applied to our cold fluid. But remember, if the cold fluid is gaining this amount of heat, then that should be the amount of heat lost by the hot fluid as well. So therefore, for the hot fluid, I have the same amount of heat, which we called Cmax. And therefore, it is going to be equal to m dot hot times Cp hot, or C maximum, C hot, multiplied by the temperature difference for the hot fluid. It enters at Th in and exits at Th out. But I don't know what Th out is. So the only unknown in that equation is the Th out that I want to solve, the minimum possible Th out, because it's based on the maximum possible heat rate. So Th out in this case is equal to Th in minus the ratio between Qmax and Cmax. So I have 110 degrees Celsius minus 836 kilowatts per Kelvin divided by 16.8 kilowatts per 836 kilowatts divided by 16.8 kilowatts per Kelvin. And therefore, our missing Th out, or the exit temperature of the minimum possible exit temperature of the hot fluid, is going to be 60.2 degrees Celsius, and that would be the answer C in our quiz. So that would have been, in fact, our quiz today, but now we can always see how it's solved, and the answer is the answer D, 60.2 degrees Celsius. So now we had one problem. We have seen our clicker quiz problem. We have one more problem to do today, and let's start doing it right now. The problem is problem 1122 in your textbook. Let's read the problem. A shell and tube heat exchanger must be designed to heat 2.5 kilograms per second of water from 15 to 85 degrees Celsius. The heating is to be accomplished by passing hot engine oil, which is available at 160 degrees Celsius, through the shell side of the exchanger. The oil is known to provide an average convection coefficient of H out. The reason why we are using out is that oil, like mentioned in the problem, is on the shell side, so it's outside of the tubes. So relative to the tubes, the oil is considered external flow to the cylinders forming our tubes. So H out is equal to 400 watts per meter squared Kelvin on the outside of the tubes. Then we have 10 tubes pass the water through the shell. 10 tubes. Doesn't mean we have 10 tube passes. We have 10 tubes. Passes means turn. Passes mean turns of the tubes. So we only have one pass. 10 tubes pass the water through the shell. Each tube is thin-walled. So that means no conduction is included in our calculation of the overall heat transfer coefficient, as you recall. So since there is no conduction, there is no fouling, so only the heat, the convection coefficients on the inside and on the outside would be considered in the calculation of our U. Each tube is thin-walled of diameter D equals 25 millimeters. That's the diameter of each of the 10 tubes, and makes 8 passes through the shell. So we have 8 tube passes. If the oil leaves the exchanger at 100 degrees Celsius, what is its flow rate? So we need the mass flow rate for the oil. The oil is the hot fluid, so therefore we need m dot h. That's the first thing we need, m dot h, m dot oil. Also, how long must the tubes be to accomplish the desired heating? So we need the length of the tubes. Very good. So let's see how this problem is done. And by the way, this problem is a little bit composite. It's a heat exchangers problem along with a convection problem. Because as you see, in the previous problem we didn't have a convection problem because we knew directly our U, our overall heat transfer coefficient. We knew it. But in this case we will have to calculate it. And we have only the heat transfer coefficient on the outside of the tubes. So we will somehow need to come up with a way to find H in, or the convection coefficient on the inside of the tubes, so that we can use the two convection coefficients and find the U. Let's see. So to summarize the problem a little bit, we have the inlet and outlet temperatures for both fluids, oil and water here. TH in 160, TH out is 100 degrees Celsius. T cool in, or T cooled in, is 15 degrees Celsius. T cold out is 85 degrees Celsius. We have m dot C, 2.5 kilograms per second, the m dot cold, but we don't know m dot hot. We need to find it. This is a shell and tube heat exchanger with one shell pass and 8 tube passes. 10 tubes are existent. Each of the tubes have a diameter of 25 millimeters, and the heat transfer coefficient on the outside of the tubes is 400 watts per meters squared Kelvin. These are our givens. What we need to find is oil flow rate required to achieve specified outlet temperature, or m dot h, m dot hot, and also we need the tube length required to achieve specified water heating, or L. We call it L, the length of our tubes. Well, let's get started. And our start point always is the properties. In the previous problem, we needed to make an assumption for one of the fluid because we didn't know the outlet temperature for it. In this case, we don't have that problem because we have all inlet and outlet temperatures for both fluids. So for the hot fluid, which is engine oil, the average temperature is the average between 160 and 100. That's 130 degrees Celsius. Convert it to Kelvin and go to table A5. That's the table that includes properties for engine oil. Cp in that case for that fluid at that temperature would be 2350 joules per kilogram Kelvin. And then the other fluid is water. The average temperature is the average between 85 and 15. That would be 50 degrees Celsius. You go to the table A6 for water and find your Cp, which is 4181 joules per kilogram Kelvin. It wouldn't hurt also to find the other properties because we are going to need them in the calculation of the convection coefficient of the internal flow of water inside the tubes. Remember that we need H in along with H out that's given to be able to find the overall heat transfer coefficient, the U. So from the table we find some more properties. The mu, or the dynamic viscosity, 548 times 10 to the power minus 6 newtons per second, Newton seconds per meter squared. Also, we have the thermal conductivity of the water, K, and that's equal to 0.643 watts per meter Kelvin. And finally, we need the Prandtl number as well, and the Prandtl number from the table is 3.56. These are the properties we would need in our problem. So now we are ready to start. And our start point is, again, making an energy balance. Again, this is a shell and tube heat exchanger, and in this kind of heat exchangers, we prefer using the epsilon or the effectiveness NTU method. So that's what we are going to do. So therefore, we start with the energy balance. We try to find the actual heat transfer, the same way we did in the previous problem, by the way. We try to find the actual Q. We try to find the maximum Q. The ratio between the two is going to be the effectiveness, epsilon. And then we try to find the NTU from there. So we start with the actual Q. You can use either fluid. No, actually, we can use only the cold fluid because that's the only fluid we have the mass flow rate for. We don't have the mass flow rate for the hot fluid. So m dot C, m dot cold times Cp cold times C cold out minus C cold in is going to be our Q, which is going to also be equal to m dot H times Cph times Th in minus Th out. And we are going to use this in the next step. So anyway, calculate the Q. M dot cold is 2.5 kilograms per second multiplied by Cp cold, and that would be 4181 joules per kilogram Kelvin multiplied by the temperature difference for the water, 85 minus 15. Then the amount of heat the water loses is 7.317 times 10 to the 5th watts. This is the amount of heat the water loses. Actually, this is the amount of heat the water gains because it's being heated up. And therefore, that is also the amount of heat the oil loses. So I would use that to find my m dot H. And my m dot H in this case, if we go back to this expression, is going to be the Q divided by Cp hot divided by the temperature difference for the hot oil, So I have 7.317 times 10 to the 5th divided by Cp for the oil, for the hot fluid, and we found that to be 2350 joules per kilogram Kelvin divided by the temperature difference for our oil, and that would be 160 minus 100, so that's 60 degrees or 60 kelvins, and therefore the mass flow rate for our hot fluid m dot H is going to be equal to 5.19 kilograms per second. 5.19 kilograms per second. So that is our first part of the problem. The oil mass flow rate is m dot H being equal to 5.19 kilograms per second. So now we use our now we have both our m dots. Now we have our CPs. So we use that to be able to find our C hot and C cold to find which is minimum and which is maximum. Therefore, C hot is m dot hot times Cp hot. We have our m dot hot to be 5.19, and this is, of course, this is rounded up, and this is multiplied by Cp hot, which is 2,350. If you do this math, then it gives you CH of 12,195 watts per Kelvin. Same thing to be done with C cold, m dot cold times Cp cold. We have 2.5 multiplied by Cp cold, which is 4,181, that's for the water, and therefore our C cold is 10,453, and therefore C cold is C minimum. That's the minimum of the two. So water is the fluid that has the minimum heat capacity. Also, Cr, which is the heat capacity ratio, is the ratio between C minimum and C maximum, or 10,453 divided by 12,195, and therefore this becomes this ratio becomes 0.857. Remember, we use the Cr a lot in the expressions that relate epsilon to NTU. Now I can calculate my epsilon. I have Q, but I don't have Q max. Q maximum is C minimum multiplied by TH in minus TC in, T hot in minus T cold in. But remember, we calculated Q, the actual Q, as m dot cold times Cp cold, which is C minimum multiplied by T cold out minus T cold in. And therefore, epsilon is calculated, the C minimums cancel each other, and the epsilon is calculated as T cold out minus T cold in divided by T hot in minus T cold in, which is the actual temperature difference for the water divided by the maximum possible temperature difference in the water. Therefore, we have 85 minus 15 degrees Celsius divided by 160 minus 15 degrees Celsius. The effectiveness of our heat exchanger is going to be 0.483. That's our effectiveness. I can use this to find my epsilon. This is my epsilon. I can use my epsilon to find my NTU. And again, I go to the table. This is a shell and tube heat exchanger, but this time it's only one shell pass. So all the hassle we had in on the two shell pass heat exchanger in the previous problem would not be used in this case. We only use two of the equations here. We only need to find our E, where epsilon 1 is just the epsilon we calculated because it was only according to one shell pass. So we just calculate the E and use the E to find NTU for one shell pass. So therefore, E is calculated as 2 divided by epsilon minus 1 plus CR divided by 1 plus CR squared to the power 1/2. Therefore, we have 2 divided by the epsilon, 0.483 minus 1 plus CR, which is 0.857, divided by 1 plus 0.857 squared, and the denominator is to the power half or square rooted. Therefore, our E is 1.74. You can use the E to find the number of transfer units, or NTU. This is equal to -1 plus CR squared to the power -1/2 multiplied by the natural log of the ratio E minus 1 to E plus 1. Then I have -1 plus 0.857 squared. All of this is to the power -1/2 multiplied by the natural log of 1.74 minus 1 over 1.74 plus 1. Our NTU is going to be equal to 0.997. So now we have our NTU, and remember, it is equal to UA divided by C minimum. Therefore, if I multiply my NTU by C minimum, it gives you the product of UA, or the overall heat transfer coefficient multiplied by the surface area. So UA, based on this, is 10,420 watts per Kelvin. Remember that I need the length. So in order to find the length of the tubes, I need to find the total surface area, and then I find the length from there. But I have a little problem that I don't have the U. I don't have the overall heat transfer coefficient. If I had it, I would just divide the 10,420 by the U and get my surface area. So I need to find a way to find my overall heat transfer coefficient. This is a thin-walled tube, so conduction across the wall is not included. The overall heat transfer coefficient in this case, so there is no fouling as well. It only includes the convection between the oil on the outside and the outer surface of the tube, and the convection of the water flowing inside of the tubes with the inside surface. So two convections. We have the convection coefficient on the outside given to us, H out, and it's 400 watts per meter squared Kelvin. But we need to find H in, and we will do the analysis for one tube. So that's going back to the internal flow convection problems we have been dealing with. I remember that would be 2 weeks ago. And therefore, as usual, I need to find the Nusselt number and therefore the H. And in order to find the Nusselt number, I need to start with the Reynolds number, find whether the problem is or the flow is laminar or turbulent, and therefore pick the right correlation for Nusselt number. Therefore, if I want to calculate the Reynolds number, then I need the mass flow rate. If I'm analyzing for one tube, I need the mass flow rate across only one tube. I have the total mass flow rate, which is 2.5. That's across the 10 tubes we have. So in order to find the mass flow rate across one tube, we take the total mass flow rate across the total number of tubes and divide it by the number of tubes. So m dot cold divided by n, where n is 10. And therefore, m dot for one tube, or we call it m dot 1, is equal to m dot cold divided by n, or 2.5 kilograms per second divided by 10, and therefore the mass flow rate for one tube is 0.25 kilograms per second, the water flow rate per tube. Therefore, I want to calculate my Reynolds number based on the diameter of the tube. It's given 25 millimeters. The Reynolds number, one of the formats for that is 4 times the mass flow rate divided by pi d times the dynamic viscosity, mu, of the cold fluid, which is water. That's the fluid flowing inside the tubes. Therefore, we have 4 times 0.25 kilograms per second divided by pi divided by the diameter. In meters, it's going to be 0.025 meters, divided by the viscosity of the water flowing inside, which is 548 times 10 to the power minus 6 newtons second per meter squared. Therefore, Reynolds number is 23,234. Compare that with the critical Reynolds number for internal flow, and it's equal to 2,300, and therefore that's obviously a turbulent flow. So since we found this to be a turbulent flow, we go to our correlation table for turbulent flows for the flow inside a circular tube. We have seen this table before 2 weeks ago in the external flow, in the internal flow lecture. So therefore, our correlations here: turbulent, 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 fully developed, fully developed, fully developed. Of course, we would assume fully developed behavior because that's the only option we have, and we will check the ratio between the length to the diameter. It should be 10 or greater than or equal to 10 for this assumption to be valid. We will check that at the end. So anyway, according to what we have here, we are going to use the first correlation because that's for Reynolds numbers greater than 10,000. This is for Prandtl numbers that are between 0.6 and 160. We have 3.56, and that is going to work in this case. We could also use the next one, but the first one is the most common and it works. All the conditions for it work. So turbulent, fully developed, Prandtl number is within this range, Reynolds number is greater than 10,000, so we can use that. The next one would give us the hassle of just trying to find more properties such as mu s, which is at the surface temperature, and we don't know that surface temperature. So we are not going to be able to use that because of the fact that we don't know the surface temperature for the tubes. So therefore, this one is easier. This one works because it fits all the criteria. The only thing that's left is to pick an n. We have n to be 0.4 for surface greater than T mean for the flowing fluid inside, and n being equal to 0.3 for Ts greater than T mean. So we don't know T surface, but think about it a little bit. What are we doing for the water? Are we heating it or are we cooling it? We are actually heating the water from 15 to 85. So therefore, the surface temperature for the tube should be hotter than the fluid for the fluid to heat up. Then T surface should be greater than T mean for the fluid, and therefore we use n of 0.4. Therefore, we use this correlation. Nusselt number at D is 0.023 Reynolds number to the power 4/5 to the Prandtl number of times the Prandtl number to the power 0.4. Let me just go back to the equation or the table of correlations for a while, because you could notice that these are for Nusselt numbers, local ones with no average sign. But here it says that you can use the Nusselt number you can use these equations to find the average Nusselt number if you use properties at T mean average or T mean in plus T mean out divided by 2, and that's what we actually use. In fact, we are using the properties at T cold average, which is the average temperature between 15 and 85, that is 50 degrees Celsius. So therefore, if we are using this correlation right here, using the Prandtl number and the mu in the Reynolds number based on the average temperature for that stream, then it would give us the average Nusselt number, not the local one, and that's what we need, in fact. So going back to the equation here, Nusselt number is equal to 0.03 times the Reynolds number to 4/5, so 23,234 to the power 4/5, multiplied by the Prandtl number 3.56 to the power 0.4. It gives us a Nusselt number of 119. Now we can use this to find our convection coefficient on the inside of the tube. So H cold, and I will call it later on Hn, it's equal to K for the cold fluid, the thermal conductivity, times the Nusselt number divided by D. I have everything. The thermal conductivity is from the table over there, 0.643 watts per meters Kelvin, multiplied by the Nusselt number 119, divided by the diameter of that tubes, or the diameter of one tube, is 0.025 meters. Therefore, the convection coefficient on the flow on the inside of the tubes of water, the convection coefficient is 3060 watts per meter squared Kelvin. Now I have my inside and outside heat transfer coefficients, and since the tubes are thin-walled, there is no need to calculate the conductive resistance. Now I can calculate my overall heat transfer coefficient. The overall heat transfer coefficient is, remember that 1 over U was equal to 1 over H in plus 1 over H out. So therefore, U is inverse that. U is 1 over H cold plus 1 over H hot. So therefore, I have 1 over, on the denominator I have 1 over 400 plus 1 over 3060. And if you do this calculation, your overall heat transfer coefficient, U, is equal to 354 watts per meter squared Kelvin. Therefore, I have my U. And I can find my tube length. Because I have UA, so I calculated UA before, it was equal to 10,420. A, the surface area, is equal to the surface area of one tube times the number of tubes. So I have pi d L times n, which is the number of tubes. That's the total surface area required. So therefore, UA is equal to UN pi dl. Therefore, if I want to calculate the L, then UA is divided by UN pi dl. UN pi d. So UA overall, it was calculated previously to be 10,420 watts per Kelvin. Divide that by the U we just calculated, 354 watts per meter squared Kelvin. Divide that by the number of tubes, 10. Divide this by pi. Divide this by the diameter, 0.02 meters. And therefore, the total length of a tube here is going to be equal to 37.5 meters. Okay, one would think that this is very long, but remember that a tube is bent 8 times. So the actual length of the heat exchanger would be this number divided by 8. But the total length of the tube with all the turns, the total length of the tube that the fluid passes inside with all the turns and all that is going to be 37.5 meters. Okay? And that is the solution for our problem. That would be the L that we need, the length that we need. That would be the end of our problem, and that would be the end of our today's class. I hope that was useful, and I hope this makes up for the fact that I wasn't here today. Anyway, I am asking you to ask all the questions you want by commenting on the video. That would be the preferred way. If you do that, please just mention the timing of the question you have. So for example, if I was saying something at 15 minutes and 33 seconds, please mention the time if you can. If you can, please mention the time in your question so that I can relate to the question, go back to the time and see what I was saying at that time, and then I would provide an answer for you. So again, please comment on the video or email me, but I would prefer that you comment on the video so that everybody who sees the video can see your question, can see my answer to the question, and everyone would benefit from that as if we were in the class today. So that would be it today. I would see you hopefully on next Tuesday, and thank you very much for watching this.